Hey, what's up, guys? This is Chung. So today, 1727, largest submatrix with rearrangements. And so you're given like a binary matrix, which means that there are only zero or ones, and you're allowed to rearrange the columns of the matrix in any order, but you have to rearrange the entire column, and you need to return the largest area of submatrix, right? And where each element of submatrix is one. And for example, right, this one here. So we have, if we move this three ones to here, then we'll have like the maximum area, right? It's going to be 4. So for this one, similar, right? Since we can move everything into all the ones together, that's why we have 3 here. And another 2, and the last one is 0. And the constraints is like this, right? So the total cells, right? Basically m times n is 10 to the power of 5. So it means that uh, it's gonna be either O of n solution or n log n solution. So with this kind of the like submatrix problems, a, a common strategy is that we need to pre-process this matrix to accumulate some ones at certain location so that we can just save some time complexity. And since for this problem, since we can move the entire row, the entire columns, so we should pre-calculate it at each of the location here, each of the position here, how many ones starting from this one. So what I mean is like this. So basically, at this location here, so we have 2 because we have 1 and a 2. So here we only have 1. So the basically I'm going to pre-calculate the at each of the locations how many consecutive ones starting from here to the end, to the bottom of the array here. That's why, so for this one it's going to be 1, right? So here's 0. So here we have 1, 2, and 3. So that's going to be the common strategy to calculate solve this kind of problem. And after having this kind of pre-calculated consecutive ones for each of the location, then we can basically we can just loop through each of the locations, right? And then we can try to calculate the area. But if we're going to calculate the area like within by using the naive way, which means that at each of the cells, let's say we know the longest ones on this on in here. So for example, if we have like this one, we have, let's say at this location here, we know the consecutive ones. Let's say we have three ones. There's 1, 1, and 1. So a naive approach is that basically we'll try to expand this length to the left and to the right, right? And the way we're doing it is we're gonna loop through to the left and then loop through to the right, and we'll only look for the what the values, right, within the same row that can have either equal or greater than the current count, which is 3. Because if there's another 3 accounts here, right, another 3 counts here, So we have 3 here, right? This is also 3 here. And then the total width will be 3 by 3. That's going to be 9, right? So but if we have like another 2 here, right? So if there's another 2 here, so here we have 2, but 2 is smaller than 3, so that's why we cannot count those column in. Yeah, and basically that's the most naive way, right? But as you guys can see that, right? So for this kind of approach, the uh, the time complexity is going to be O of n cube, right? So let's say the n is like either the length or the width, because to loop through all the cells we need n square, and for each of the square we also need to loop through the entire row, right? That's another n here, and this will TLE, right? So how can we improve that? I mean, our purpose is what? Our purpose is trying to find an efficient way to calculate the area so that we don't have to recalculate it the same column uh, over and over. So what we can do is like this. So for each of the row here, right? So if you guys take a closer look here, we can sort the values right on each row by the from the biggest to the smallest. And why is that? Because let's say we have 3 here. We have 2 t 3 3 and 2 2 2, right? So if we sort this row from the biggest to smallest, we're gonna have like 3 3 3 and then 2 and 2. Since we can rearrange the column freely, so which means that we can always try to rearrange the columns, right, to with the biggest count to the beginning, so that after this one, the column we can get is like this 3 3 3 2 and 2. So after sorting this one, now at each of the locations, all we need to do is that, so the area is equal to what? So the area is it's going to be the current values, going to be the value, right, times the index, which is j plus 1. Because, since we're sorting uh, in the descending orders, so let's say at the current location here, right? So it means that, at this location, the consecutive one is 2. But how many other columns can have at least same like consecutive ones? It's actually the length x no, it's actually the length of the current index, which is the j plus 1, because all the numbers before this index is gonna have the either equals or greater than the current consecutive ones. That's why we can after sorting we can calculate the uh, the area within O1 time by using this formula. Right? Because if I give you an example here, so let's say we have not this one, maybe another one. It's going to be like let's say we have 4, 5, and 3, right? So 4, 5, 3, and 2. So if I draw like a diagram like this, so we're gonna have like 5, 4, 3, and 2. This is like 5 consecutive ones. That's why at each of the locations, right, at the rectangle areas, it's kind of obvious, right? So because this is because everything on the left is greater than the current one, so that's why with this length, with the current length, the biggest, the current biggest area with this current number as the height is going to be the index. This height, for example, is 4 times the index plus 1. In this case, it's going to be 4 times 2 equals to 8, right? And the same thing for 3 here. So it's going to be 3 times 3 equals to 9. Here is like 2 times 4 equals to 8. And we just need to get the biggest value out of all this kind of areas. Yeah, so actually the coding is kind of, it's not that long. So basically what we need is that we're going to have like a matrix, have the length of the height of the matrix, right? And the so here I'm going to create like a count, right, to store the the pre-processed values. You know, actually you can reuse the same the matrix, I guess, do a in-place updates, but I'm just using a new one to make this code a little bit easier to read, you know. Range. Basically, I'm allocating the same size of that, right? And then to pre-process, so for j in range of n, right? Because for each of the columns, we're going to add up the ones from bottom to top. That's why I'm going to do a for I in range of n minus 1. Yeah, I guess you can also do it top down. You know, I believe you'll get the same result, but I'm just since I'm using this kind of concept, right? Starting from here until to the bottom. That's why so we're gonna have the counts at the beginning, right? So if the matrix of I and j is 1, right? And then we just do this. Otherwise, if it's 0, we can simply skip that, right? Which means that it's going to have 0 consecutive ones starting from here. So if it's 1, then we just we will have 1 at the beginning. Then if I is smaller than n minus 1, right? And then it will count dot ij accumulates the counts of I plus 1j. Okay. So now we have like a pre-processed counts array here. So we can simply we can just start populating the final answer. So which means that we can have like an I in range of m, right? That's going to be the rows, and we need to sort, right, the values on each of the row here. So I'm going to have like a sorted count, right, equals to sorted and count dot I, and then I'm going to sort it in the descending order. And for j in range n, right, answer equals the max of answer dot, it's going to be sorted count dot j times j plus 1, and then return the answer. Okay. Okay, accept it, submit. Okay. Yeah, I mean, so in time and space complexity, right? I mean, time complexity is actually, so we have like a O of n square here, and here is just so it's not of n square. Yeah, because here with sort is a n log. Oh, actually, sorry, it's not n square. It's a O of n square log n. Yeah, I'm assuming, right? I'm assuming the n and the m, they are like equally they're kind of the same. So we have a like m here, right? So let's say this is m, right? So m times actually the so here is actually it's a log n log n to sort, right? sort this to sort these counts. That's why it's going to be a m times n log n. Yeah, because this n log n is greater is have a bigger time complexity than n here. Mm, yeah, I think that's it, right? So I mean, for this kind of matrix submatrix problem, it's always a common strategy to pre-process some values based on each of the locations. And since we are so for this problem, since we are like we can uh, reorder the columns, and then it kind of makes sense to pre-process the consecutive ones. I mean vertically. And after that, so here you need a little bit trick to be able to find like an optimal way, right, to iterate uh, all the rectangles to calculate the area at each of the location. Since we cannot do it brute forcefully, like we cannot for each of the locations we just iterate the entire row, right? That's gonna be too slow. That's why we just use one of the common strategy, right, with this kind of sub-matrix problems. Since the one of the key features for the sub-matrix problems that if we sort the the consecutive ones from the biggest to the smallest, then at each of the locations here, as long as we know the index here, right? So we can easily get the biggest area, right, with the current consecutive with the current height, which is the values, the height times the j plus one. And yeah, and I think that's all it needs to solve this problem. Mm, cool. I think I'll just stop here. And thank you for watching this video, guys. Stay tuned. See you guys soon. Bye bye.